Hello, everyone. So most of you guys are here, so we'll get started. Let me open my PowerPoint here. All right, so a few reminders here. Homework 8 is due tonight, 11:55 p.m. And then number 8 is online now. Should be due next Wednesday, 11:55. Okay, so you guys still have some time from now to submit your homework number 8. Okay. And then exam 3 will be happening on April 15th, the Wednesday after we come back from the Easter break. Okay, so that's the plan for the next couple of weeks. We'll still be looking at chapter 16 here. Today we'll be checking on section 6 in this chapter. Okay. This is on instantaneous center of zero velocities. Okay, so objectives are here. So two objectives. First, locate the instantaneous center of zero velocity for the object. Okay, and then second, use this instantaneous center to determine the velocity of any point on the object. Okay, so activity here again we'll be starting with reading quiz and applications, and then on the lecture part, and then to look at a couple concept quizzes and attention quiz. Okay, and then a couple examples after that. If there's still time, we can look at the group problem solving. Okay, so let's get started with the reading quiz here for extra credits. All right, go ahead and do those two and send me your answers in the chat privately. Okay. Sorry, I think I was unmuted. I was muted, so I just unmuted. So you probably didn't hear me, but yeah, we'll start with the quiz here. Send me your answers privately, okay? All right, just a final call if you haven't submitted your answers. Okay, we are going to close this quiz in say 20 seconds. All right, I think everyone just submit your answer. Okay, so let's take a look here. The first one says, if applicable, the method of instantaneous center can be used to determine, the answer would be just A, okay? Could be used to determine the velocity of any point on the rigid body, okay? So you can only use that to determine velocity, not velocity and acceleration, all right? The second one here says the velocity of any point on a rigid body should be perpendicular, okay, to the relative position vector extending from the instantaneous center to the point. Okay, so A and B. All right, I think everyone got second one right, but a couple of you guys didn't get first one right. Okay, so A and B to be the answers for the reading quiz. All right. Let's see. All right, so let's get back to the application. Close out the chat window on my end here. You probably don't see that, but okay. So, so in this section, we will talk about instantaneous center of zero velocity. Okay, so that's the full definition, instantaneous center of zero velocity. So that means when a body is having rotational motion, it could be general motion, which include rotational motion and translation motion. Okay, so then at certain instant, there will be a point on the body, or maybe outside of the body. Okay, and a point that is actually having zero instantaneous velocity. Okay, so for example, if you are riding a bike, so the wheel that is in contact, the point on the wheel that is in contact with the ground, that is actually a point that is having zero instantaneous velocity at given moment, okay, at the instant. So, so then in that case, if you look at the wheel as a whole body, then any point other than that point of contact, actually we are rotating with respect to this point, okay? So that's what happens when you have a rotational an object that is in rotational motion, okay? So, so in that case, then whichever that is having the longest distance from this point will have the maximum velocity, okay? So for example here, should be the top of the wheel, you'll have the longest distance to the instantaneous center of zero velocity. So then that guy will have the largest linear velocity, okay? And then this guy will be having zero, okay? Now, in other cases where the instantaneous center of zero velocity might not lie on the body of the object itself. So for example, if there's a stick here, slides down from the wall over here, so you can see at this point, this is a point B here having velocity, this guy having velocity. So the body, the whole body here, there will be every point on the whole body would have non-zero velocity, okay, because it's in the having motions there. So then in that case, you can still locate an instantaneous center of velocity, which is outside of the body here. Okay, we will talk about how to do that later. But that's a scenario. You have actually an IC that is not located on the body. Okay, so let's get to the lecture part of this section here. So if anybody undergoes planetary motion, that means translational motion along with the rotational motion. Okay, so then there exists a point in the plane of rotation at which the velocity is instantaneously zero. Okay, so we call it IC. Okay, and as the case we checked earlier, it may not lay on the body. Okay, so in that case, all right, so I think we are going to talk about how to determine the IC just in the next slide. Okay, so you will see that, and then there's a case that we can see why it's not on the body. Okay, so if a object is having general planetary motion, okay, so then the fact, okay, so the IC, because for IC it's always at that instant that has zero velocity. Okay, that's the point. Okay, so to locate IC, we need to use the fact that the zero at this point on the body is always perpendicular to the relative position vector from the IC. Okay, so that means the position vector is perpendicular to the velocity, okay, because the body is rotating with the IC point. Okay, so then in that case, this is zero velocity, so that means this is the rotational axis. Okay, so position vector over here, if you draw it, velocity should be perpendicular to that. Okay, so this is one of the facts. So these two should be always perpendicular to each other. Right. So the first scenario that you might have is the velocity, the direction of the velocity is known. Okay, so if direction of the velocity is known for a point, particular point on the body here, and then the magnitude, you also know it. Okay, so and then so that's one known velocity as known, including position, including direction, and then magnitude. Okay, and then also if you know the rotational velocity omega, then you can locate where the IC is. Okay, so you basically will be drawing a line that is perpendicular to the velocity. Okay, so this line here. Now, if the body is rotating in this direction, then the IC should be somewhere on this side, not on the other side. Okay, because that makes it rotate in that direction. All right, and then for the length of this r vector, then you are going to use the relationship that v is equal to omega times r, or r is equal to v divided by omega. Okay, so then that gives you the length of it. So you can determine where the IC is given the velocity and then also the angular velocity. Okay, so this is one of the scenario. Okay, if you know velocity and angular velocity of the particular point on the object, then you can locate its IC. Okay. Also, if you know two velocity, or if you know the velocity of any 2 points on the body, then you can also locate the IC, the instantaneous center of zero velocity. Okay, so given say for point A and point B, you know their velocities. Okay, then you are going to draw a line perpendicular to VA. All right, and then also a second line perpendicular to VB. All right, at point B, starting from point B and then point A. So the two lines intersect would be the location where the IC is. Okay, so this should be the IC of the object. So in this case, you can see the IC may be laying out of the body. Okay, and then this is the same scenario as the stick we checked earlier when it slides down the wall. Okay, so if you take 2 points, then you can actually draw lines perpendicular to the velocity starting from the 2 points. Okay, so that's how you calculate or locate IC in the second scenario. Okay, so second scenario, you know VA for point A, you know VB for point B. Okay. The third scenario you may have is if the two velocities, the 2 points on the body have velocities that is parallel to each other. Okay, so it could be in this case or it could be in this case. Okay, then given the fact that you know their velocity, the magnitude, okay, and directions, so then you are going to just connect the two, the head of the two vectors. Okay, so VB vector, VA vector, and then also A and B. So then the line, the blue line here, intersect with line AB, which will give you the location of IC. Okay, in this case, you are going to back extend AB and then connect these two. So these two will intersect over here. Okay, so this is a scenario where you have IC on the body. This is where you have IC outside of the body. Okay, so that's the third scenario when you know the two velocities are parallel to each other. Okay, how you are going to do it, locate your IC. All right, so those are the three scenarios. Now, once we locate our IC for the object, okay, then you can use the IC to determine the angular velocity of the object at that time instant. Okay, so for example, if you are given, say, point A, the velocity of point A, and then you determine this is your IC, then the omega should be equal to velocity divided by this R, A to IC. Okay, and then that omega should be shared by all the other points on the body. Okay, or the whole body. Okay, because the whole body is rotating with respect to this point, the point of IC. Okay, so then omega will be the same. You can use the same omega you determine from point A, and then you can use that to calculate velocity for point B and point C, etc. Okay. All right. Now let's look at the concept quizzes here. All right. And then the attention quiz is right after this. So I'll just create the breakout rooms. You guys can discuss on both the concept quizzes and also the attention quizzes, okay? And let's see. I'm going to create 4 rooms, okay? Yeah, and then I'm going to close out the breakout rooms in a few minutes, okay? Say 5 or 6 minutes, okay? So let's do that. All right, so I have closed the breakout room, so all of you guys are back. So let's take a look on the concept quizzes here first. The first one says that velocities of 2 points on a body are equal in magnitude and parallel, but in opposite directions. Okay, so this is the scenario then we just checked earlier, but this time you have say opposite A and B, so A and B like that. Okay, and then velocity is VA in that direction, and then VB in that direction. Okay, so if they are equal in magnitude, then if you connect the head of the two velocities, okay, it will happen to be at the center of the 2 points. Okay, the midpoint. So then this is C. Okay, on this one it should be C. On the second one here, it says when the direction of velocity of the 2 points on the body are perpendicular to each other. So say this guy A and B here. Okay, so A and B. So if so I don't know, let's say if A is going in say in this direction, right? So VA, then VB will be either in that direction or the other way around. Okay, so they're in that direction, say there in that direction, or this direction. Okay, whichever. But so to determine the IC on this one, then you want to have the line perpendicular to this guy, right? So if this is this one, then the line perpendicular to VA will be in this direction. Okay, and then you draw a line perpendicular to B, VB, so it should be in that direction. Okay. So then in this case, right? So it could be, if you look at this case, okay, so then it looks like it's going to be at point B, right? But in general, that this is just a special case, but in general, you might have, say, VA in this direction, right? So A, and then B could be in that direction, all right? So VB in that direction, VA in that direction. So then if you draw a line here, perpendicular to this guy, and then this guy will be perpendicular to this, okay? So, so this is a more generalized case, okay? So it's not either A or B, it's not on any of this here, okay? So it could be somewhere here, and it's not on infinity, okay? So if you draw a scenario like this, then you might get an answer like say B, one of the 2 points, okay? But in general, more general scenario, this is the case, okay? So B is just a special case. It doesn't cover all the scenario, okay? So on this one, I think all I guess says D, so this is right, okay? So D will be right. All right. Now let's look at the attention quiz. Okay, some of you guys have sent me your answers to attention quiz. Some of you guys don't, but let's take a look here together. So let's look at number 1. So number 1 says the wheel shown has a radius of 15 inch. Okay, so let's do the attention quiz here. 15 inch, and then rotates clockwise at a rate of 3. Okay, what's VB? All right, so now this is an application of the IC to figure out what's the velocity at point B. Okay, so let me see some more answers for this. Okay, got that. So in this case, if this is real rotating with angular velocity of 3, okay, so it tells you, it indicates that VA is the 0 velocity point, okay? So then you can pick that as your IC, instantaneous center of 0 velocity, okay? So then any point on the wheel should be rotating with respect to VA, okay? So in this case, let's see, so if the radius is 15, all right, so then we are looking for velocity at point B, okay? So this guy, point B is over here, okay? So then you will be doing, all right, so let's do it this way, okay? So RB with respect to IC, that's 15 inches, all right? Now omega is 3, so if it rotates with 3 angular velocity, okay? So then let's take a look here. Yeah. So then your VB should be equal to the omega times this, okay? So omega times RB with respect to IC, right? So that should be 3 times 15, okay? It should be 45, okay? Inches per second, all right? So this is D here. Okay, let's see. Some new responses here. Let me just take a quick peek on this one. All right, yeah, so you guys all says D. Okay. Now let's look at point quizzes 2 here on the attention quiz here. So it says point A on the rod has a velocity of 8 meters to the, let's see, my screen is covering that. Okay, to the right. So where's the IC of the rod? Okay, so here you're going to see, because this guy is going to the left, right, or to the right here. So this is the velocity. So you want to just draw the line that is perpendicular to this velocity, okay? Now from the figure here, from the geometry here, you can see this guy is being confined in this slot. So VB is going to be going downward, okay? So then you are going to draw through B the line perpendicular to VB, okay? So then the point C, these two lines intersect at point C. So then point C will be your IC for the rod, okay? So that's from the geometry. So this guy is C, all right? Let me see. Yeah, so you guys said C, okay? So that's right, okay? Good job, guys. Okay. Now, let's take a look a couple of examples here. So the first one says the linkage undergoing motion as shown here. The velocity of the block VD is 3 meters per second. Find the angular velocity of links AB and BD. All right, so we're looking for angular velocity of this link over here, and then also this guy. Okay. So let's see how we actually can solve for this one. So the plan here is to locate the instantaneous center of zero velocity of link B and D, okay? So B and D, because we know velocity of this guy is 3 to the right, okay? Now, look at this point B, all right? You'll realize that because this is linkage A and B, so then this will be rotating with respect to this point A, okay? So on point B, it should have velocity that's perpendicular to the linkage, all right? So then if you look at point, look at this rod B and D, at given moment, okay, this rod will be rotating about its IC center of instantaneous center of zero velocity, so which we can determine what would be that, okay? Now, the instance showing here that this angle is 90. So then for B, because it's rotating about this point A here, for B, the velocity is going to be along the BD because this guy is 90, okay? If this is rotating about 1x at any point, its velocity is tangent, okay, to the to this R. Okay, so that means 90 degree to that R. Okay, so then it's naturally given this is 90 degrees. So then the VB will be in the direction of B, pointing from B towards D. Okay, so then in this case, if you draw a line perpendicular to VB, I think it's the next slide shows here. Oh, actually, yeah, over here. So whatever I just said, it's about this guy here. Okay, the solution's here. So VD is in this direction, VB is in this direction. So then you're going to draw a line through point D perpendicular to VD. So it goes in this direction. And then this guy going through this, all right, point B perpendicular to VB should be in that direction. Okay, so the two lines will intercept at some point over here, all right, which is this figure shows. Okay, so this is where the direction that is perpendicular to VB through B. Okay, and then this is the line that going through D perpendicular to VD. Okay, the two intercept at this point. Okay, and then given the angle is 90 degree, so then also in the figure earlier shows that this rod makes a 40 degree with the horizontal, so then also 45 degree with the vertical line here. Okay, so using the facts here and then also looking at the geometry, we can determine that so if this is 0.4 meter, then this guy should be also 0.4 meter. Okay, because this is 45 degree, this is 90 degree, this should be also 45 degree. Okay, and then this should be square root 2 of 0.4, which is 0.4 divided by cosine 45, which is 0.566. Okay, so then these two radius of them are determined. Okay, so then the omega for BD, because then BD, this rod should be rotating about its IC over here, okay, with the angular velocity omega here, all right? Given this as 3 meters per second, and then this guy, the R of this guy is given, so V divided by R should give you omega, okay, BD, all right? So omega BD can be determined by doing VD divided by R point D to IC. So 3 divided by 0.566 gives you 5.3 radians per second. Okay, this is for BD. All right, once BD, omega BD is determined, you can use that omega BD to figure out the velocity at point B. Okay, so then we'll be looking at linkage AB because the velocity of point B will be determined, okay, by using this omega times this radius or this position vector length. Okay, then you have VB. So VB will be determined as 2.12. So basically you do 5.3 multiplied by 0.4. Okay, 0.4 is this length, RB to IC, multiplied by omega BD gives you that velocity. Okay, so then that velocity is the same velocity on point B here on the linkage AB. So then using that velocity, you should be able to determine this omega AB. Okay, so omega AB is VB divided by RBA. Okay, again, VB is equal to RB to the AC times omega BD, right? And then divide by that. So that gives you also 5.3. Okay, it just happens to be the same. Because this is 0.3, this is also 0.3 or 0.4. I'm sorry. The length of AB is 0.4. The RB slash IC is also 0.4. So then the two omegas are the same in magnitude. Okay, they do rotate in the opposite direction.
Dr. Ho?
Yes.
So you said that just happens to be the same. So that's not always the case that it would be the same, given that
right.
A is fixed and not moving.
Right. So yeah, this is just for this geometry, given the numbers, the angles, so it happens to be the same. But one example would be AB. If AB is not the same length as BD, then the two R's wouldn't be the same. Okay. And then the geometry. It's just the numbers given here tells you that those two radius are the same. Okay. But in other scenarios, say AB is 0.4, BD could be 0.3. Okay. Then the whole geometry changes. All right. So because point B it's rotating with respect to A at this instant, okay? And then it's also rotating with the IC of BD, okay? So the AB length is not always the same as B, the distance from B to IC, okay? So that's something you want to keep in mind, okay? So it's just because this geometry happens to be the same for the two, okay?
Gotcha.
All right. Cool. So then let's look at example 2 here. So given that center O of the gear set rolls with V0 at 6, all right, and then the gear rec B is fixed. Okay, so then we are looking for the velocity of point A on the outer gear. Okay. So in this case here, we can locate the IC easily because by looking at the contact point of the smaller gear with this the rack here, gear rack over here, because at the point of contact for a gear here with this fixed, right? This fixed gear over here. So at the point here, because if you look at any point on the gear rack B should be fixed, right? It's not moving. So then the contact point here shouldn't be moving as well, okay, at that instant, okay? So then this point would be your IC center for the gear set, including the small one and the larger one, okay? So you can take that as your IC. Let me see if the next slide shows that, yes. So here will be your IC because that's the point where at this instant that the velocity is equal to 0. So then the whole gear set is going to rotate with respect to this IC with the angular velocity of omega, okay? Now we can determine omega easily by using this velocity of VO divided by this length, all right? And then we can use that omega to determine this velocity, but we have to figure out this distance of R from A to IC, okay, this guy. But it can be determined from the geometry as well, okay? So first, the solution tells you the omega, it can be determined by doing VO divided by R from O to IC, okay? So that's the radius of the smaller gear. So 6 divided by 0.3 gives you 20 radians per second as the angular velocity of the whole gear set with respect to IC. Okay, now we can use that multiplied by this length, the R from A to C, to figure out this VA. Okay, so VA then will be equal to R. In this case, it actually use vector. Okay, but you don't necessarily have to use vector. You can just use the length of this guy. Okay, or the length of the AC by looking at the geometry. It should be 0.3 square plus 0.6 square and then square root. Okay. But in this case, I think if you are doing vector here, it also gives you the x and y components. That means the direction also it's indicated by this expression. Okay, so if that's the case, I think it's looking for velocity. That's why the solution, yeah. So it looks for velocity of point A. That means you want to determine the magnitude and direction, or you can express in the forms of the yeah, in this guy. Okay, so then you can determine the magnitude by doing the x component square plus the y component square, okay, and then the direction angle as tangent inverse of the y divided by x, okay. If you are doing vector quantity here again for omega, if you express it's a vector, so then this should be the so given the omega as the clockwise direction, you are going to use your right hand rule. Okay, so your right hand rule is going to tell you that the direction of the omega vector is in the direction of your thumb, so it's pointing into the screen here, which means negative k direction. Okay, that's why this omega here, when it plugs in the number, it says minus 20k. Okay, so minus 20, that means your omega direction of your omega vector is actually pointing into the screen, which is the negative k direction. Okay, so pay attention to the sign over there for the negative sign here. Now for the R, A to IC, then it's this guy, okay? So this is IC, so the X component, because this is towards the left here, so it should be minus, okay? Minus 0.6, and then upward to be positive Y, so positive 0.3 J, okay? So then you're doing cross product, okay? So cross product of, if you have 20 minus 20 times minus 0.6 gives you 12, all right? And the direction is K cross I. K cross I gives J. So that means 12J, okay? 12J there. Minus 20K now cross 0.3J, okay? So that gives you 6, minus 6, okay? But K cross J will give you minus I, okay? So then it's positive 6I, okay? 6I plus 12J, all right? So then you can determine the directions over there, okay? So this is the second one. Let me see what time is it now. Do we have time for the group problem solvings? Okay, so let's take a look on that. A couple of minutes, a few minutes here, we can have a quick look on this one, I think. So this one says, given that CD, all right, it's rotating with an angular velocity of 4 radius per second. Or let me ask if you guys have any question on the second example here before we actually talk about the group problem solvings. All right. So if not, then let's look at this one here. So this is 4 radius per second. It's asking you to find the angular velocity of rods AB and BC. Okay. So you can see here. So AB. So then for point B, this is rotating with respect to point A. Okay. So then for VB, velocity of B for either rod AB and BC, it's going to be perpendicular to this guy, the radius, okay, or the position vector. So if this guy is rotating to the right or the counterclockwise direction, then you can see it will push this in that direction, okay? So then this guy will rotate in a clockwise direction with respect to A, okay? And then the velocity of C here will be in that direction. All right, so let me just show you guys quickly how we can solve for this one. And then I'll be posting flow solutions later on the PowerPoint, okay? So draw it quickly. So assuming this is all we have. So this is point D, this guy is C, B, A, okay? So, and then this is 30 degrees. So velocity for B should be in this direction, VB, okay? And then VC is in that direction, okay? So for the rod B and C, you can find its instantaneous center of zero velocity by drawing a line going through C but perpendicular to VC, okay? And then also, this is perpendicular to that, so then it should be somewhere here. So this should be the IC for rod BD, okay? So we can figure out VC by given that the DCD is rotating with 4, okay? So then VC should be equal to 4 times the CD, the length of CD, which is given as 0.5, okay? Will be omega times R, omega of CD times R of CD, okay? So that gives us 2 meters per second for VC. All right, so once we have that, we can figure out what's the omega BC, this whole rod rotating with this instantaneous center of zero velocity. So then that would be equal to VC divided by RC to its instantaneous center, okay? So RC here, you can figure out what's this length, R of C to IC, because this is 30, that means this guy is 30, okay? And then we know the length of BC, let me see, where is that? Yeah, BC is 0.4, okay? So if BC is 0.4, RBC is equal to 0.4 meters, then this guy would be 0.4 meters, R of C to IC would be 0.4 meters times tangent of 30, okay? So if you do that, this is going to be equal to 0.231 meters, all right? So then this is equal to 2 divided by 0.231 meters, okay? Take that into that expression over there. So then omega BC is 8.66 radians per second. That's omega, okay? All right, so we have found omega BC then. Now we can find the velocity of B by using that, okay? So velocity of point B should be equal to omega BC times R of B with respect to the IC, okay? So in this case, this is the RB to the IC, okay? So again, we are given this guy, we are given this angle, we can figure out this R, okay? So RB IC should be equal to 0.4. This is the side, this is the angle, this is hypotenuse, okay? So it should be 0.4 divided by cosine of 30, okay? So that would be 0.462 meters, all right? So then 8.66 times 0.462 meters, that will give us the velocity for point B to be 4 meters per second, all right? Use that 4 meters per second, we should be able to figure out the omega AB, okay, by using RAB. So VB also is equal to omega AB times RAB, okay? RAB is given as 1 meter there. So this is 4.00 meters per second equals to omega AB times 1 meters. So omega AB then is 4 radians per second, okay, or 4.00, okay? So that's how we are going to do it, okay? Yeah, this one is pretty similar to example 1, okay? Any questions you guys might have on this? So it's about, again, it's about geometry and then also identifying the IC, okay? So if you guys don't have questions, then we'll stop here for today, okay? So your homework is due tonight at 11:55, all right? And then I will see you guys on Friday. Bye.
Bye. Have a good day.
Bye, have a good day.